Okay, so angular momentum is I times omega. What happens if so I've got something spinning, it has a moment of inertia. It depends on its shape, right? Okay. Going back, these guys. These are all the shapes of things, and it's not only the shape of the object, but where you rotate it around. Because if I take this pole right here and rotate it around, it has a moment of inertia, this. And if I take the same thing but rotate it around this point, it has this moment of inertia, right? So if I change the shape or where I'm rotating things, then I've changed I. Okay. Now, what I'm claiming is that if I change moment of inertia of an object, it'll have some impact if it's rotating. So moment of inertia, or sorry, angular momentum, L is the letter we use for it. I know that's a little confusing, but L is the angular momentum. I get I times omega. So if angular momentum is conserved, we can say I in the beginning times the rotational velocity of the object in the beginning should equal I in the end times omega in the end for an object. Okay. So think of if I have my hands out and I was spinning around. Okay, so I have some I. I'm spinning around like on a chair, for instance, and I have some angular velocity spinning around, and then I change my shape by pulling my arms in. Have I changed I? Yeah, because I changed the shape. I changed how things are rotating around. So I've changed I. So what should happen in effect?
The angular velocity.
Angular velocity is going to change.
So it should speed up, right?
If I decrease I.
Yeah.
If I is, in the beginning, let's make up a number 20, and then this is 1.
Yeah.
Okay? 20 times 1 is 20. If I change this to 10, if I change I to 10, this has to change to 2. Does that make sense? In order to, because 10 times 2 is going to give me 20. Okay? And very, very unusual things can happen with that. Okay? Which I want to talk about now with conservation. So I have a couple of videos here. Turn up the volume. And skip this ad. This has nothing to do with regular. Now notice here, law of conservation of angular momentum states that if no unbalanced external torque acts on a rotating system, the angular momentum of the system is constant. Okay. When we said that momentum is conserved, we were talking about there was no outside forces. Okay. A simple way to say this right here is if there's no outside, instead of forces, I need rotational force. What do we have for rotational force? What's equivalent to force but in rotation?
Is that the moment of inertia?
That's equivalent to mass. Moment of inertia is equivalent to mass, rotational mass. What's force equivalent to? It starts with a T.
Oh, it's a torque.
Torque, yeah. Force is like torque. So if in conservation of momentum, there are no outside forces, then I have conservation of momentum. Well, in order for there to be conservation of angular momentum, I need no outside torques.
Yeah.
Okay? So notice what's happening here. So what was going on in that one?
More moment of inertia.
when his arms are what?
When his arms are out.
When his arms are out, he has more moment of inertia, and then he decreases moment of inertia by bringing him in. And what happened? What was the effect? Sped up. Yeah. So here's another kid doing it. Okay. So here we go. She's got this wheel here. She's standing on a little disc. And I want to kind of explain what's happening here. Watch. So they're going to spin it. Now she doesn't do anything right now, right? But then she rotates.
That's pretty cool.
How's she controlling herself?
She's not doing anything, she's just changing the angle of the wheel.
She's changing the angle of the wheel, and that causes her to spin, right? Okay, so what's actually happening here is that wheel is spinning like this, right?
Yeah.
Okay. So angular momentum, if you can use your right hand to figure out what direction angular momentum was going. Now at the beginning, the wheel was upright. Let's see if I can get to that. Okay. Right here. Okay. So the wheel is upright.
Yeah.
So how much angular momentum does she have?
0.
0. This wheel has 0 angular momentum, and she's not spinning, so she has 0 angular momentum. Now, they're going to spin the wheel in this direction, right?
Yeah.
Okay. So how do we figure out what way the angular momentum is going? Well, the way you do it is you actually take your fingers on your right hand, has to be your right hand, okay?
Yeah.
Okay, it's called the right hand rule for that reason. And you bend your fingers, except your thumb, okay, so you're kind of putting your hand out flat, and you bend your fingers or curl your fingers in the direction of rotation.
Yeah.
Now, it's not that way because the wheel is like this, right?
Yeah.
So put it like how it's going. So curl your fingers along the direction of rotation. No,
But with the wheel.
no, the wheel's not rotating like this. The wheel's rotating like this, right?
Like.
Which way is the wheel rotating? It's rotating like this. Is the wheel rotating like this?
No, it's going.
So point your fingers in the direction of the rotation. No, it's not rotating like that. You're pointing this way. You're pointing into the board. Do you see that?
Oh, when we go with the board.
Alright, here's the wheel, okay? It's rotating in this direction, okay? So point your fingers in that direction. Go ahead, do it.
Really, it's the board.
Yeah, relative to the board, like that. Now curl your fingers in the direction of rotation. It rotates like that, right?
Yeah.
Okay. Which way is your thumb pointing?
This way.
Yeah, which way? Describe it.
It's the board.
Into the board, okay? So that tells you the direction of angular momentum. That direction is actually into the board.
So if you're spinning the wheel this way, it's going to the left.
Yes, it's going into the board.
So what if you spin the wheel the other way? It's going
So if you spin the wheel, instead of going around this way, like they are doing in the video, they spin the wheel going this way. We put our hand out and we curl our fingers in the direction of the rotation. I can't curl my fingers backwards, right? Okay, so I have to flip my hand upside down and then curl this way. Now which way is the angular momentum going? It's going out of the board.
Yeah.
Okay, so it's telling you what direction it's going. Now, she's going to switch, so we've got, so how much angular momentum is there before? There's 0.
Yeah.
Okay? Now, think of this disc right here. If this disc starts rotating, let's say it rotates around this way. Okay? So put your hand and curl your fingers around in the direction of rotation. Okay?
Yeah.
If it's just this foot disc, right, it's going down. If there was some rotation. And if it rotated the other way, it would be going up, right? Okay. It's just a memory technique. They could have called it the left-hand rule if they wanted, and then everyone uses left hand. And then everything would be flipped the other way, but everyone has to agree on it.
So if you were going, so you have to go down when you do that?
What's that?
If you're going right and this? And you
Yeah, if the wheel is spinning like this, okay, you put your hand down and rotate, so the angular momentum is going down in that case.
Yeah.
Use your right hand. There you go, it's down.
So it's not really physically possible with your left.
Correct, it's not possible, because it's not called the left hand rule, it's the right hand rule.
Well, like you couldn't go like this and have your thumb up here.
Correct.
Yeah.
Okay. Now, if the disc on the bottom was rotating like in this direction, then you curl your fingers and your thumb ends up pointing upward, right? Okay. So let's see what happens and kind of explain. So how much momentum, angular momentum, is there in the system before rotation?
None.
None. Okay. Now we're spinning it. Now there is angular momentum, right? Which way is it going? It's going into the board.
Yeah.
Okay. Now she's going to do something. So in the up and down direction, how much angular momentum is there?
None.
There is none. She's not rotating on her disc, right? And this thing's angular momentum is into the board, or into the video, if you want.
If the wheels going this way, why would they go left?
Well, we're
Like,
going to start
towards
looking
the
at
right.
this is just a way to remember it so that we can understand what happens. And there's a lot of physical, unusual things that happen. Okay, so let's see what she does first. Okay, so she turned it. She rotated the wheel to the right. Which way? The angular momentum was coming out of the disc. It was upright. It was going into the board. When she spun it up like that, which way did she point the angular momentum?
She was going. The wheel's going this way.
Mm-hmm.
So she
Yeah.
started turning the wheel.
Right, so it started, so if you start the right hand rule with the initial position, she was going like this, right?
Yeah.
Yeah, so there was angular momentum into the board or into the video. And then she rotated the wheel, so just rotate your hand the way she rotated the wheel. Now which way is the angular momentum going? Up, okay? Now, so now she has, in the upward direction, there's a component. There's some of the angular momentum is going upward, right?
Yeah.
Okay, some of it's also going to the left, but some of it's going upward with the angle that she's going. So some of it's going up. And now which way does she rotate?
To the right.
She rotates to the right, so let's put our hand down. And it's her angular momentum down here is going this direction. So if you use the right hand rule, which way is the angular momentum going? It's going down. Which way is this angular momentum going?
Somewhat up.
Somewhat up. The component that's going up, however much that is equal to the angular momentum going down. Notice they're in opposite directions.
Yeah.
One's down, one's up. Why? Well, this is conservation of momentum. If I add up the two angular momentums, they equal 0.
Yeah.
It's physics happening right now. Physics is trying to conserve angular momentum.
So she's not going to go up or down. She's just going
She'll either rotate left or rotate right. Now, if the wheel started spinning, okay, like if someone started spinning the wheel and she was able to rotate, she would rotate in the opposite direction. Like if you were able to just start spinning the wheel, and there was some, like she was in free space or something like that, then she would start rotating like around her hips. Does that make sense? And it would rotate in the opposite direction, but there is no axis of rotation in that way. We actually have an outside torque. There's friction on her feet that's causing her to stop rotating around in that circle. I don't know if that was the right way, but when she initially started, the second that kid started spinning the wheel, she would start spinning in the opposite direction to conserve angular momentum. But we have an outside torque because we have friction that's stopping her feet from coming out from underneath it. Does that make sense? So when she's
But she's on a disc that rotates, right? So wouldn't she start turning?
So the only, her body right here is only able to rotate around in a circle like this or around in a circle like this. That's it.
She can't go up and
She can't rotate around like this. But if she was in space,
yeah.
if she was in space and someone started rotating that wheel, that stuff would start happening because it would still conserve angular momentum. Okay? So now let's see what happens continuing on. Okay, so she goes that way, and then she flips it. Now which way, when she turns it to the left, now the angular momentum of this disc is now going a little bit down towards the ground, right?
Yeah.
So in order to compensate, in order for there to be conservation of momentum, it has to rotate in the opposite direction. So her rotation this way, if you put your hand around it, you'll see that the angular momentum is now upward, while this angular momentum is now downward. And if you added up their angular momentums, they would be exactly equal to each other.
Yeah.
Does that make sense? It's kind of interesting. So she can completely control which way she goes, left or right, by just changing the angle of that wheel. Does that make sense?
Seems kind of like how plane steers and that kind of thing.
Planes use this thing right here.
Just
We'll
if
talk
it's
about it.
banks, it turns.
We call them gyroscopes. I'm gonna get a gyroscope in here Thursday, but we might have to wait till after break before we demonstrate it. I'll show you a
I've seen
video.
one before. It's
Yeah, but I'll show you a really cool one on the video here in a few minutes. But planes use gyroscopes as well, and we'll talk about why that is.
they like all planes, which is really good ones.
All planes, they use gyroscopes.
Is it like built in the, or is it like in the front or the back or?
So if you were in space and you wanted to rotate an object,
Yeah.
you could use just a spinning wheel and change the orientation, and then the spacecraft will actually move. And that's actually how they do move things.
They use gyroscopes too.
Yeah.
But it doesn't like, you can't actually like move, you can just change your position.
You can change which way you're facing.
Yeah. You can't actually go a certain direction. So the gyroscope's pretty useful.
Absolutely. So that's the law of conservation of momentum. Pretty interesting. It looks like magic. Let's go
So
back.
it's the same thing as kind of what segways do too, right?
Segways use that principle too,
Keeps
actually.
them up as well.
Let's go
I
here.
love segues.
So let's see this gyroscope video, because this one's pretty interesting. It's an older video, but it's really cool.
This is an experiment with a spinning wheel, a rather large wheel, 13 inches diameter, mounted in a ball bearing on a shaft 3 feet long. I am going to hold it like this and swing it in a circle and lift it with one hand, but only when it's spinning. First of all, let me weigh it to show you just how heavy it is.
Here's the scale.
As I talk, you'll see that lifting it is quite an effort. It weighs about 40 pounds, and I can't lift it any higher than that without a lot of strain. So now we'll spin it up to 2,500 revs a minute,
Okay.
which
2,500, so 2,500 RPMs.
That thing, that's what,
2,500 RPMs.
I would want to stay away from that.
Yeah, he'll talk about how much energy that is.
when it becomes a live thing. Then I shall lift it 5 feet in 3 seconds by going round in a big circle.
So he's using a little drill to get it spun up.
Whilst I'm doing it, I shall talk to you.
There's a ball bearing inside. There's a ball bearing inside there, so his hands
I
are.
think that hurts
Yeah.
him.
Tell from my voice that I'm not under any stress of any kind.
You should see this. Stay for a second. So how fast is it going?
2,500.
2,500 RPM. So that thing you wouldn't want to break apart because it'll kill you. Additionally, stopping it sucks. But so it's got an immense
And
amount of
then I shall
angular
let go with my left hand, and holding this remote end of the shaft only, I shall lift the wheel through 5 feet, all on its own with no effort on my part. All I do is apparently just to steer it along a path that it's already decided it would like to go. Then there's the question of how you stop the wheel. That speed, that wheel has enough energy to throw itself 200 feet in the air. Did you notice that as it went round in a circle, there was no centrifugal force trying to pull my arm out sideways? Let's just do it once more. To save time, we've already spun it up. So here goes 40 pounds of wheel as light as a feather. This is not a conjuring trick. This is a fact of science. Watch it again carefully. The fact about the spinning wheel, so far, everyone has missed.
Okay. So
Why does he only go around once? Why doesn't he just keep going around? That would look cool.
he could keep going around.
It's too dangerous.
No, he could. I'm sure he doesn't want to lose his balance.
Yeah.
And I'm going to show you one more video here, because this right here is what he was doing right there was basically a gyroscope that he had. Okay, he was part of that gyroscope. But you can see how gyroscopes work. I'll have one here for you next week. I can spell gyroscope. Okay. This is not a gyroscope, obviously. So that thing he was spinning was basically, and I want you to see it, I want you to think about it, it's basically like a gyroscope. This is the wheel
This is a
that was
gyroscope.
spinning, okay?
It
And then
consists
there's
of
an
a wheel
axis
mounted on
going
an
through
axle.
it.
So you
The wheel
control.
and axle.
So the axis is like that
secured in a
arm
metal
that he was
frame.
holding on to.
Yeah.
Okay, he was kind of holding, like, think of it as bigger, he was right over here, and then this thing was spinning. So it's going to be able to do the same thing, except it's a little bit, it's not as impressive because it's not so heavy, but it does something that's very cool.
This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over.
Okay, now why does it fall over? Because the center of mass is above, above the foot, so it's going to fall
It's
over.
like right in the middle.
Yeah, if you wanted to balance it, you'd have to actually get the mass right above its feet. That's when things topple over, is when their center of mass is beyond their feet, beyond the base of the object, and that's happening here, that's why it's falling.
Well, if you have like a really low spinning top, it goes like right over the ground. And it's
So,
balance.
and this one, obviously, it's not doing anything, so here's its base, and the center of mass is right about here, so gravity's pulling downward, so it's definitely going to fall to the ground, right?
Yeah.
You'd have to have it upright, and then maybe it'll go over, maybe you can balance it, but probably not, because the base is really, really small. In order to exactly balance something, the center of mass has to be directly over its base.
Yeah.
Rocks.
Kind of impossible.
Yeah.
Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel.
That was like the guy standing at the end
Yeah.
with the machine that was spinning it out.
The first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright.
Okay, so that's like a top.
When the wheel stops, the force disappears and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating.
So now take a look at, compare that to what he was just doing. It's the exact same thing.
Yeah.
Normally gravity would be pulling down. Gravity's still pulling down on it. But the only reason why it's doing this, and this is called precession, as it's rotating around, is because of, in fact, you saw him, he was rotating around the same way, right? If he spun the top the other direction, it would precess in the opposite direction.
Yeah.
What it's doing is it's conserving angular momentum as it's doing this. Okay.
So like a normal spinning top wouldn't touch the ground already, but the stand allows it to go over more.
Yeah, bend over. So it's literally, I mean, it's like a balance.
A spinning gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one
So
end.
it's spinning, and you lift it up. Notice the precession there. That precession has to happen in order for it to do this.
Yeah.
In order for it to conserve angular momentum.
This interesting behavior is difficult to explain.
No, it's not.
Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has.
So it has to rotate in those
To
directions.
change the direction of the stone requires a force.
Yeah.
Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation.
It's kind of like mass in that way. Mass resists its change in velocity. This gyroscope will resist its change in position.
And if the wheel is spinning really, really, really fast, it wouldn't really move at all, right? It would move really slowly.
No, it would still precess. It would precess a little bit faster.
Oh.
The fact that gyroscopes will maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position. If the aircraft rolls, electric sensors and contacts connected to the gyro send information to the pilot about the air.
So this is important. When we get into a plane, when we
Oh,
actually
that's how
do
the
flight-
navigation works.
Yeah, when we actually get into the plane, the first thing you'll notice is when he starts up the plane, you'll hear this loud whirring noise. It'll be like,
That's the gyroscope.
that's the gyroscope spinning up. And the point of it is so that you'll have a little horizon bar on a plane. I mean, it does a few other things, but the horizon bar is one of the main ones. Is actually when the plane banks, the gyroscope will stay upright because it resists that change. And so you can always,
It doesn't actually balance the plane. It just tells you.
it tells you which way is up.
Yeah.
Yeah.
So then
Correct
you can balance the
orientation.
plane.
So it stays in its position.
What about up and down?
The Mars rover explores the surface of Mars using spinning gyroscopes to provide stability and navigational information. This full-sized robotic helicopter flies without an onboard pilot. Gyroscopes provide stability and navigation. Gyroscopes have become essential components of aircraft, ships, robots, and spacecraft. If you're interested in experimenting with a gyroscope, they are available from online science and hobby retailers. The gyroscopes I'm using are manufactured by Titco Manufacturing in Hagerstown, Indiana. They are identical to toy gyroscopes first manufactured over 90 years ago.
It's not a new thing.
More science
No.
and technology-related videos can be found at our website,
Okay.
Follow the project's link.
Let's get back to that guy. Okay. So, gyroscopes work based on the principle of conservation of angular momentum. They also work on the fact that if you recall, a force equals change in momentum over time.
Yeah.
Okay. It also works out, gyroscopes work off the principle that torque equals change in momentum over time. That change in momentum that you're seeing there, that gravity's applying a torque to those gyroscopes to make them fall down to the ground.
Yeah.
Okay, it's applying a torque. So that means there has to be a change in momentum. And the change in momentum is that rotation that you're seeing there. Change in angular momentum. I'm sorry. So let's go on to this guy. This problem we were discussing yesterday. So an object rotating on a string changes the length of the string. A small mass n is attached to the end of the string, revolves around a circle on a frictionless tabletop. The other end of the string passes through the hole in the table. Initially, the mass rotates with a speed of 2.4 in a circle with radius this. So I'll draw my tabletop. Okay, so there's a hole in that tabletop, and there's a string that dangles down underneath it, and there's a string over here with an object, and that object's rotating around in a circle. Can I do vectors with this guy? this guy has a velocity of 2.4 meters per second as it's spinning around. And then what are they doing? They're actually pulling down, and that's shortening the string. Okay. The reason why there's going to be a conservation of momentum is because there's no outside torques. There's nothing speeding this object going around, and there's nothing slowing it down as well. Okay. But what are you changing by by pulling down on the string?
Moment of inertia.
The moment of
It's
inertia.
getting closer to the center.
It's getting closer to the center. Okay. So momentum is conserved in this, and we can figure out what it is. Okay. Now we can consider this to be a point mass. Okay. A point at the end of the string. Okay. So we don't have to use any of those equations like a sphere or something that's rotating. We can just use the basic mr squared to figure out its moment of inertia. So let's do that. Okay. So I1 omega 1 equals I2. Oops.
Another thing, how do they keep the gyroscope from line spinning? And there's no,
Just a little draft, electrical draft.
it has to be magnetic though, right? You couldn't actually.
No, you can just have like a little thing that's spun.
Like, is that what it is?
Yeah, it's just a little motor that's doing it. Okay. So I've got angular momentum in the beginning, should equal angular momentum in the end, because I have no outside torques on this system. Okay, there's nothing slowing it down. It's important to realize the table is frictionless. If the table wasn't frictionless, we'd have a problem.
So like air holes.
Yeah, like an air hockey table. Okay. So what's the initial moment of inertia for this object? Well, it's its mass, which we said was m, and the radius of the string, which is 0.8. So that's going to be m times 0.8 squared times its initial angular velocity. What did they give me? Did they give me angular velocity in the beginning?
Speed.
They gave you speed. They gave me linear velocity. I need to translate that into angular velocity in order to use it in this equation. Do you remember the equation to use?
Go from linear to angular?
Yeah. It's V equals omega R.
So yeah, so you're going from,
V equals.
so you're just adding, you're multiplying the
So
linear velocity by the radius, and that'll get you.
no, we multiply the angular velocity by the radius and we get the linear velocity. The units should work out. What's the units for this? It's radians per second. Remember, radians is unitless.
Yeah.
Times a length, which is meters. So radians per second times meters gives you meters per second.
Yeah.
Okay. Go ahead and pull out your calculator. 2.4 equals omega, which I don't know, but I do know the radius is 0.8. So omega in this case is going to equal 2.4 divided by 0.8.
It seems like in the textbook, when they give an answer in revolutions, it's always in minutes.
Usually we measure things in revolutions per minute.
So it's kind of confusing.
2.4
If you're using radians, it's going to be per second. Or it should be per second.
It is per second, yeah.
And if you're doing revolutions, it should be minute.
Usually. 2.4 divided by 0.8.
Yeah. 3.
3.0.
I just got 3.
Okay, so 3.0. Have to add 2 sigmas. Okay. So this one right here is 3 point, actually, I carry an extra, so it'll be 3.0. That doesn't really matter, it's not going to affect things. Equals, what's its moment of inertia when I pull that string down? Well, it's going to change it, right?
Yeah.
Okay. So it's now going to be its mass times its new radius. What's its new radius? 0.48. Squared times that angular velocity. Okay. Now notice they asked me what is the velocity when that's not angular velocity. So I'm going to have to take whatever answer I get here and change it into linear velocity. Okay. Notice they didn't give us the mass, but there's masses on both sides, so they cancel. So I'm going to do 0.8 squared times 3 divided by 0.48. And what do I get from 948? So this squared times this divided by this squared times 3 divided by 0.48 squared. Okay, that sounds about right. 8.3, two sig figs. Actually, I'll do another 3. Radians per second. Okay. I need to now translate that into velocity. What's the new speed of the object? Well, I can use this equation again. So v equals omega r. The velocity of the object is going to be 8.33 times the new radius, which is 0.4. What do I get from my velocity? You got the calculator.
4.
4.0. Does that answer make sense? 4.0 meters per second.
So was it not?
It was at 2.4 meters per second, and now it's at 4.0 meters per second. It was going around in a circle at a slow pace, and then when I decrease the radius of the object, it now goes at a faster pace.
Seems like so you decreased it by about half. So it's sped up by like twice as fast.
And you can't use that because we've got the squared term inside r, so it's not always true. Okay. But that's how we get an object. Change it. Okay. Because angular momentum is conserved. Let's take a look at this one. Okay. A star collapse. Astronomers often detect stars that are rotating extremely rapidly. Yeah, stars rotating fast. Known as neutron stars. Neutron stars are interesting in their own right because if you actually take a tablespoon of it, it's going to weigh something on the order of about 10,000 pounds, like a teaspoon. Neutron stars are very dense.
So what is it like becoming a black hole? Or?
No, it didn't have enough mass to become a black hole, but it was almost a black hole. Okay. These stars are believed to have formed from the inner core of larger stars that have collapsed due to their own gravitation.
And why does it happen? Just
So much stuff, gravity's pulling on it so hard that it's actually compressing everything. Compressing it so much that it's changing the atoms in it to neutrons. Okay.
it seems so weird because it wasn't doing it before.
Yeah, it just had enough mass, like it was so heavy that more stuff was falling into it. To a point, right before it collapsed, it actually it collapsed so much that it caused a nuclear explosion because you've got atoms colliding at that point, and it sprays off a lot of mass when that happens. And you get left with a neutron star. Okay, before the collapse, the core of the star is the size of our sun, so it's the size of our sun, with a mass 2 times as great as the sun. So it's twice as massive. And it's rotating at a speed of 1 revolution every 10 days. That's pretty fast. Okay. So 1 rotation on Earth is 24 hours, so it's not as fast as Earth, but it's still fast. If it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, if it was going from that amount of kilometers to 10 kilometers, what would its rotation speed be then?
Should be a lot, right?
So, do you see how this is very much like a conservation of momentum problem? It's like those people who are putting out their arms and then bringing them in.
Yeah.
That's kind of the same thing that's happening here. You have a star with its arms out, it's at this radius, and then it collapses by bringing its arms in to 10 kilometers.
So it brings stuff in so it gets closer to the center, so it spins faster.
So it's going to spin faster, so we want to calculate what that speed is going to be. Assume the star is a uniform sphere at all times. Okay.
Yeah.
So let's do this problem. So it's a conservation of momentum. We have no outside torques, it's just like the kids who are bringing their arms in. The angular momentum in the beginning equals the angular momentum in the end. I need to calculate I for the star in the beginning, right? And omega is, well, it's 1 revolution every 10 days. So it's 0.1 revolution per day. so let's figure this out. Okay, let's get I. We need to know the moment of inertia for a sphere. For a sphere, it's 2/5 mr squared.
Yeah.
2/5 the mass of the whole thing. Okay. Which did they give us? I don't think they did. Mass 2 times greater as the sun. And I don't think it'll matter, or I'll just say the mass of the star is this much. Okay.
Yeah.
Times the radius of the thing. 7 times 10 to the 5th, which normally I'd convert that into meters instead of kilometers, but I'm leaving in there because I think it's going to work out, and I'll show you why it's going to work out if I just leave it in kilometers. Okay. Equals, now it's a new sphere, okay, it's a smaller sphere. Oops, I forgot something. 2/5 mr squared times omega. Now omega is in revolutions per day. Okay, I should convert that to radians per second normally, but I'm going to leave it in revolutions per day. Okay, equals 2/5 the mass. The mass didn't change, right? It just collapsed. Times the new radius of 10 kilometers. Times omega. I don't know what omega is, but I'm looking for it. Oops, sorry, that's going to be squared. Yeah? Okay, masses are going to cancel. They didn't actually matter in this problem. 2/5 are going to cancel. Okay. Now notice this is in kilometers. I'm going to be multiplying this by a conversion factor in order to get it into meters, right? And then I'm squaring that. So that conversion factor is just a number that I'm multiplying by. A number squared. This I'm going to multiply by that same conversion factor and I'm going to square it. So if you want to think of it, I'm just going to make up a letter. I'll call it A. It's going to be A squared over here. This number times A, so I'm going to square it. This number times A, and then I square it. So there's going to be an A squared on both sides. So those A squareds are going to cancel out when I solve for omega, isn't it?
Yeah.
So
you can get rid of the squares.
well, the A squared, the conversion factor. Right here, I should have taken this and I multiplied it by something in order to get meters, right?
Yeah.
Let's call that number A,
Yeah.
okay? And then it's squared, so it's going to end up being, I'm going to have an A squared over here.
Yeah.
Does that make sense? But this one right here, I'm just going to multiply by that same A, and I'm going to square it, so there's an A squared over here.
So you can get rid of the 2 A squares.
Right, so I didn't need to convert them, is what I'm explaining,
Yeah.
okay? Because they're going to cancel out anyway.
Yeah.
Okay, so the answer is 7 times 10 to the 5th.
But the answer will be in kilometers.
The answer is going to be in revolutions per day,
Oh.
because this answer right here is in revolutions per day. Times 0.1 divided by 100. 10 squared is 100. That's going to be my new omega.
So just 7.
7 EE10,
Yeah.
or EE5 squared. Make sure to put parentheses around it.
What, the E5?
7 E5.
Well, the calculator's not soon enough.
I don't know, maybe.
You wouldn't risk it. Times 0.1.
Divided by. $4 million.
9,000.
So 4.9 times 10 to the
6. And then 6.
6 revolutions
And then
per day.
that's a lot.
Yeah, it was slower than Earth, and now it's way faster than Earth.
Yeah.
Okay. Does this make sense?
Because it got that much smaller.
It got that much smaller.
It used to be really huge and tiny.
This is not your homework, but you now have homework. I'll post that up there. Let me stop the recording.